Generating a highly detailed 3D chair is a solved problem. Generating the room it sits in, with the floor plan, the surrounding architecture, and the collision physics required to walk around that chair, is an entirely different class of computational challenge. When standard image to 3D diffusion models are forced to scale up to environment sizes, the representational capacity breaks down. The latent space stretches too thin across the scene, producing an unplayable, fused mass of geometry. A game engine cannot process a melted painting. It requires strict traversability. A character needs mathematically defined physical boundaries, collision meshes, and a precise path to navigate without falling through the floor. Meta Reality Labs developed a solution called WorldGen. It takes a single text prompt and outputs fully textured, functional, and traversable 3D environments ready for engines like Unreal or Unity in under 5 minutes. They achieve this by linking 4 distinct stages: large language model layout planning, procedural generation, diffusion-based 3D reconstruction, and autoregressive scene decomposition. By breaking the problem down, WorldGen avoids the trap of monolithic generation. The system generates a coarse physical layout first, decomposes the assets, and refines them individually. To build a functional world, WorldGen operates like an urban planner. It establishes structural zoning and physical pathways long before considering the building's aesthetic details. The user provides an unstructured text prompt. A large language model parses that text and converts it into a rigid JSON schema, explicitly defining parameters for terrain type, verticality, and object density. Those parameters feed a procedural generation algorithm. It applies Perlin noise to generate terrain, computes boundaries using binary space partitioning, and drops in placeholder bounding boxes. This raw, rule-based geometry forms what is called the blockout. It serves as a strict physical scaffold for the scene. From this blockout, WorldGen extracts a Navmesh. Using algorithms like Recast, it calculates the exterior surfaces and guarantees a continuous, mathematically verified walkable path through the environment. With the physical layout locked, the system renders an isometric depth map of the blockout. This depth map conditions a diffusion model to generate the initial 2D reference image of the scene. Altering the procedural parameters directly manipulates these depth maps, resulting in reference images that span from flat, sparse encampments to highly vertical, dense city grids. By the time generative AI begins hallucinating visual details, the physical laws and navigational constraints of the simulated world are already hard-coded into the layout. To translate the 2D reference image into a 3D volume, the system acts like a blindfolded sculptor, molding a landscape using specific physical anchor points. Asset Gen 2, the backbone of this reconstruction, relies on a highly compressed 3D format known as the VecSet latent representation. VecSet uses farthest point sampling to extract exactly K tokens, forcing geometry through a bottleneck. These sparse tokens receive spatial encoding. Through cross-attention, a transformer decodes those points back into a continuous volume called a signed distance field. For WorldGen, the Asset Gen 2 architecture is modified. It must denoise the latent volume while strictly conforming to both the visual reference image and the previously extracted Navmesh. The Navmesh is embedded as a sparse point cloud. Additional cross-attention layers are injected directly into the diffusion backbone, forcing the generated geometry to warp and fit the predefined traversable paths. Processing the entire scene holistically ensures contextual logic. Chairs spawn next to tables, not on roofs, while the explicit Navmesh conditioning guarantees the final mesh remains physically navigable. A monolithic 3D scene is practically useless for interactive development. It must be broken into individual assets, fracturing a fused cluster into distinct pieces. Meta developed AutoPartGen to handle this autoregressive part extraction. Initially, the model generated parts sequentially, which proved too computationally expensive for environments containing dozens of assets. The optimization comes from calculating the connectivity degree. The system scans for pivot parts, geometry that physically collides with the highest number of other objects. In a landscape, this is almost always the ground plane. By generating and isolating these massive pivot parts first, the remaining geometry is left floating. The system can then use simple connected component analysis to rapidly slice the remaining structures apart. Training a model to identify these breaks required a massive dataset. Meta utilized a vision language model to scan internal asset libraries, expressly mining for complex scenes and isolating topologically connected components to teach the algorithm where parts should naturally separate. This ground-aware reasoning drops the decomposition latency from 10 minutes to under 60 seconds, cleanly isolating distinct buildings and trees from the terrain. Decomposing the monolithic mesh links generative context and modular game design, allowing developers to select, edit, and move individual assets within the engine. Separated assets are initially low resolution. They require a targeted upgrade, studying a master reference map to restore fine details to a weathered relic. Each isolated mesh is rendered and passed to a large language vision model. Crucially, the VLM is also fed a top-down view of the full scene, with the target object highlighted, ensuring the new high-resolution details remain stylistically coherent with the surrounding environment. A specialized mesh refinement model encodes the coarse mesh into latents, concatenates them with noise latents, and runs them through the diffusion process. This injects high-frequency geometric details while strictly preserving the object's original orientation and scale. The final hurdle is applying a texture. Packed, complex geometries suffer from self-occlusion. Standard projection methods leave deep crevices and hidden angles completely unpainted. WorldGen solves this by generating textures directly in 3D using a process called disentangled multi-view attention. This splits the attention block into 3 streams. In-plane attention handles the local detail of a single view. Reference attention locks generated views to the VLM image. Finally, multi-view attention allows the generated angles to check against each other, wrapping the texture consistently. By isolating the refinement phase, the pipeline injects massive visual fidelity into individual props and structures without violating the rigid procedural blueprint established in the very first step. This chart shows the chamfer distance comparisons between WorldGen and baseline image to 3D models. By measuring the physical deviation between the target layout and the generated mesh, the data proves WorldGen achieves up to a 40 to 50% tighter alignment to the required navigational paths. On the decomposition side, the optimized connectivity degree sorting yields an F-score of 0.853, achieving precise part segmentation in under a minute. When placed alongside leading monolithic part generators, the difference is stark. Alternative models fragment buildings into unusable shards, or fail to separate the terrain from the structures entirely. Other generative approaches, like Gaussian splatting, produce impressive visual fly-throughs. However, splats are clouds of colored points. They lack the explicit polygonal geometry and collision data required to actually walk a character through the environment in Unity or Unreal. WorldGen does have constraints. It relies heavily on Meta's proprietary 3D datasets for training, and the 5-minute processing window means we are still a step away from real-time, on-the-fly world generation during active gameplay. Yet the architectural solutions are highly effective, merging strict procedural rules with generative flexibility, forcing diffusion models to obey Navmeshes via cross-attention, and relying on an auto-regressive coarse-to-refine pipeline solves the fidelity problem. It stops treating 3D generation as the creation of passive sculptures. By enforcing the laws of physics and traversability first, WorldGen proves that generative AI can successfully output rigorous, functional architecture for interactive realities.